Hello, in this session I'll be going through combustion analysis calculations. The background theory is that we have an organic compound that is unknown, and we want to work out how much carbon, hydrogen, or even oxygen, or maybe nitrogen is in our organic compound. So what we want to be able to do is react it with an excess amount of oxygen, so it burns completely. We obtain a massive carbon dioxide and water, and the values that we can then use will be able to help us in calculating the carbon, hydrogen, or oxygen or nitrogen in our organic compound. So any carbon dioxide produced is then absorbed by a soda asbestos type substance, or it could be a mixture of calcium hydroxide or sodium hydroxide to absorb the carbon dioxide. The water can be absorbed by an anhydrous drying agent such as magnesium chlorate or calcium chloride anhydrous, and the idea is that we obtain the masses of water. So in this case, solid X will absorb water and solid Y would absorb the CO2. And so that we can work out, after weighing before and after, how much was produced. And then from that information, we can work out an unknown compound A. So it says here, the percentages of carbon and hydrogen in an organic compound can be determined by weighing the products after complete combustion. We want the air to be dry, in this case just oxygen, so dry oxygen going through, because we don't want any added values of water in the products, because otherwise we'll perceive that as being more water produced. So example question, a mass of hydrocarbon produced that mass of carbon dioxide and that mass of water. Calculate the empirical formula of the compound. So we have 0.0234 grams of our hydrocarbon, so that means it contains only carbon and hydrogen. We react it with an unknown amount of oxygen to produce CO2 and water, and we have a mass of carbon dioxide and a mass of water produced. So it is always good practice to show the examiner when laying out your working. So mass of carbon is equal to 12 over 44 times 0.0792 grams of CO2. Doing 12 over 44 because this mass all adds up to CO2, and as a fraction of the formula, we have carbon and two oxygens, so carbon being 12, and the total MR molar mass of carbon dioxide is 44. So the percent by mass, that is carbon in this compound, would be 12 over 44. So 12 over 44 times that mass will give us the mass of carbon, which would be 0.0216 grams. And then we can get the moles of carbon by then just dividing that value by 12. That would give us 1.8 times 10 to the minus 3. We can do the same thing with water. So if we take the percent by mass, so 2 over 18, because there's two hydrogens, they're one each. That's 2 divided by 18 is the fraction of which the mass would be in relation to hydrogen within water. And so the mass of hydrogen would be 2 over 18 times the mass of water, and that would give us mass of hydrogen. What we are aiming to do is to get the number of moles of each, because if we have the moles of each, then we can get the ratio between them, which is what this type of question wants us to do. So there's only 1 for the relative atomic mass of hydrogen, so 1.8 times 10 to the minus 3 divided by 1 will give us the moles of hydrogen as being 1.8 times 10 to the minus 3. People make a mistake here by dividing by 2. If you divide by 2, then you're going to get moles of hydrogen. And we don't want moles of diatomic hydrogen, and most people get drilled in or used to the fact that hydrogen goes around in pairs, in which it does when it's molecular hydrogen. But what we're trying to do is just get the moles of hydrogen atoms, and that's the important part here when people can go wrong, is that we want the moles of hydrogen atoms and not diatomic hydrogen molecules. So now we've got the moles of each, we can then determine the empirical formula by dividing each by the smallest number of moles. In this case they're the same, so that divided by 1.8 times 10 to the minus 3 is going to be 1. That divided by 1.8 times 10 to the minus 3 is also going to be 1. So the ratio here tells us that the empirical formula is 1 carbon, 1 hydrogen, and just CH. You can get extended questions that then say that the molecular mass of the organic molecule is 78. What is the molecular formula? So what this is saying is, if we know what the empirical formula is, and by definition, empirical formula is the simplest whole number ratio of elements in a compound, then if the actual molecule is 78, how many times does this empirical formula go into 78? And so what you then need to do is work out what the MR is of the empirical formula. In this case, it would be 12 plus 1 is 13. And if the actual molecule has a molar mass of 78, then 78 divided by 13 will say to us that the empirical formula goes into it 6 times. And so if we then multiply the empirical formula by 6, so carbon times 6 and hydrogen times 6, that tells us the molecular formula is C6H6. Also, just watch out for any units for the molar mass. So sometimes it will present it as saying the molecular mass of the organic compound is 78 grams per mole, or grams per mole written in that way. What they're saying is the MR of the molecule is this. What is the molecular formula? And so you'd have to do the question where you work out the empirical and then apply that to work out what the molecular formula would be. So the next example is an example that also contains oxygen, so it's not just a hydrocarbon. So an organic compound X contains carbon, hydrogen and oxygen. 0.104 grams of this unknown compound X is burned completely in oxygen to produce 0.072 grams of water and 0.176 grams of carbon dioxide. So again, the only way you can really work this out is by working out the mass of CO2 and water. Don't try to work out if you have been given the formula of organic, in this case organic X, because most questions would want you to show by calculation and not just trial and error of balancing an equation. So we know that the mass of CO2 and water is produced as those values, so we proceed in the same way. So mass of carbon is 12/44 times that mass. That gives us mass of carbon, and mass of hydrogen would be 2/18 times 0.072, and that would give us that mass of hydrogen. So we need to work out the mass of oxygen, and the only way to do this is by first obtaining the mass of carbon and hydrogen, because we don't know how much oxygen there is as a ratio in our organic compound X, as well as we don't really necessarily know how much oxygen we've added. So what we need to do is work out the mass of carbon and hydrogen first. And so if we know our organic compound X has a mass of 0.104 grams, and the mass of carbon and the mass of hydrogen are those, I should just say that, sorry, plus 8 times 10 minus 3 grams, then rearranging to find X will give us the value of X, at this case being 0.048. And this will tell us the mass of oxygen, because the organic compound contains carbon, hydrogen and oxygen. If we know those two, then and the organic X, then we can rearrange to work out what the mass of oxygen would be. So subtracting the masses of carbon and hydrogen gives us 0.048. And then what we need to do is again work out the moles of each. There is an alternative way to get the moles of carbon and hydrogen, and sometimes people might prefer this. So I'll do this quickly before we move on. So to get the moles of carbon, well, we have done this method where we could just do that divided by 12, and this method where the mass of hydrogen divided by 1. But you could do 0.176 divided by the MR of CO2, which is 44, and that will give you moles of CO2, appreciating that all the moles of carbon would be the same, and so that value would also be the same. You could do 0.072 divided by 18, and that will give you moles of water, and then appreciate that for every 1 compound of water, you've got twice as much hydrogen within it. So you need to times that value by 2 to get moles of hydrogen as atoms. So that's an alternative method to do that, and then you can get the masses of 8 times 10 to the minus 3 by then, in this case, timesing by 1. That will give you the mass of hydrogen, and then you could do the moles of carbon, because that would be the same as CO2, times by 12 would give you 0.048. So either method would get you the same sort of values that you need, but to maybe avoid making a mistake, stick to the percent by mass. So that's an alternative method to choose to do it instead. So we've got mass of carbon, mass of hydrogen, and we've also now got mass of oxygen. So if we want to work out the ratio, the empirical formula, then we divide them all by their relative atomic mass. So carbon is 12, hydrogen 1, oxygen 16. Another mistake here that creeps in is that, again, people assume oxygen is diatomic. I don't know why they're assuming that. That is what it is when it's existing in standard conditions, or just as a molecule of oxygen. But we're not trying to work that out. We're trying to work out oxygen atoms, because we don't know what the ratio is within our organic compound X. So we're always trying to work out the atoms, the moles of atoms, not the molecules. So hydrogen again would be 1, not 2. So carbon 0.048 over 12, hydrogen 8 times 10 to the minus 3 over 1, and oxygen 0.048 over 16. That gives us those values for the moles of each. And then what we want to do is divide them by the smallest number. And so if we do that, we want to divide each by, say, 3 times 10 to the minus 3. That gives us 1 oxygen, 2.67, hydrogen, 1.33 of carbon. So this isn't a whole number. So what we need to do is to multiply them to make them into a whole number. So they're a third, roughly, and 2/3 for hydrogen. So if we multiply them by 3, each of them by 3, that is, it's too significant to just round down to 1 or round up to 3, so we need to apply this ratio to get a new whole number, which is going to be 4, 8 and 3. So that means we've got 4 carbons, 8 hydrogens, and then we have 3 oxygens. So our empirical formula is C4H8O3. If you can't quite see that, then I guess you could do trial and error, times them by 1, and then work out, obviously, that's not going to fix it. Times them by 2, that still won't fix it. Times them by 3 will give you pretty much the whole number now. So each of them multiply by 3. So now it's time for an exam question, which you might want to have a go yourself. So you can pause the screen on here, and I'll go through the answer very soon. So pause now. And the answer will happen now. So if you haven't had the chance to do that, pause it, But here we go. So we have a question where we now actually have carbon, hydrogen, oxygen, and nitrogen. And the mass of the organic compound X is burned in oxygen as normal. And we get our values for mass of water, mass of carbon dioxide, and in this case, mass of nitrogen. So this one actually is more challenging. We are presented with even more information where you should know that under standard conditions, 1 mole of any gas will occupy the same volume, in this case 24,000 centimetres cubed or decimeters cubed. So this means the amount of volume per mole. Calculate the empirical formula of compound X, that's what I've been doing before, and the molar mass of X is 132 grams per mole. Deduce the molecular formula, so I said that at the very beginning, and then show how we arrived at our answer, so that's through calculation. So that's an additional mark for that point. The one before that would normally be about 4 marks. So the mass of organic X is burnt in oxygen to make CO2 and water, and so what I want to do is work out mass of carbon. So mass of carbon, 12/44 times 0.176, that's going to be the mass of carbon. Do the same for hydrogen, that's going to be my mass of hydrogen. And then for nitrogen, well, I have the requirement to use moles equals volume over 24 or 24,000. Depending on what unit I'm working in. If I'm working in centimetres cubed, then that'll be 24,000. So the volume that I have been presented with is 24. So in this case, I want to do 24 over 24,000. And that's going to give me my moles of diatomic nitrogen. Because yes, this is how it was collected as diatomic nitrogen. But what I then want to do is get moles of nitrogen atoms. So if I times that by 2, because I want always the moles of nitrogen atoms, and I'm going to want the mass of nitrogen because I also need to work out the mass of oxygen. So in these questions, just be careful as to what you need, because not always would you need oxygen or nitrogen, but carbon, hydrogen, oxygen and nitrogen are all within my organic compound. So now I've got the moles of nitrogen atoms, must always need atoms, timesing by its relative atomic mass of 14 will give me the mass of nitrogen atoms. If I did previously 1 times 10 to the minus 3 times by 28 for diatomic nitrogen, that would give me the same value, which will be 0.028 grams. It all depends on perspective as to what you want. In this case, if I had known what I was doing, then it didn't really matter what route I took. But just to remember that we want eventually the moles of nitrogen atoms when we do the calculation to work out the empirical formula. So now we've got mass of carbon, hydrogen and nitrogen. So that's my mass of carbon, mass of hydrogen and mass of nitrogen. It's always good to show the examiner what your values are. So again, mass in brackets carbon equals, or mass in brackets hydrogen, and that way they can easily go through your working. So the mass of oxygen now, which you should leave to last, so don't work at oxygen until you've got the rest of them, rearranging the equation. So the mass of our organic compound X would be the mass of carbon, hydrogen, oxygen and nitrogen. And now we have carbon, hydrogen and nitrogen. We just need to rearrange to get oxygen. We also have our organic compound X. And so after rearranging, it comes out like the previous question actually, 0.048 grams of oxygen is how much you'd have of it. And then we're now at the stage where we want to find the moles again. So what we want to do is get the moles of everything. So divide by 12 for carbon, 1 for hydrogen, 14 for nitrogen, although we did it earlier. Oxygen, divide by 16. And then we get the moles of each. And then you want to divide them all by the smallest number of moles. A mistake can happen here where you're using mass values instead of moles. So always, again, make it clear to yourself as to what they are. Putting in a column format like this as a table might also help. So working them out as follows will give us 2, 4, 1 and 1.5, and that's not a whole number, so we can't again ignore that. We can't just round that to 2, so that means we have to double everything. So when we double everything, that's going to be making that a whole number of 3, and then everything else is also a whole number, and so that means that's our empirical formula is C4 8 hydrogens N2O3. And in the previous part of the question, it said that the molar mass of organic compound X is 132. So what you need to do is add that up, which I believe comes up to 132 as well, which means the empirical is both its molecular formula as well as being its empirical. And then we have shown that by adding that up. And that's it. So if you want more chemistry support, then feel free to check out the other videos and subscribe, and I'll be adding more when I can. Have a nice day.